extend until about 10 minutes after 4, or I should stop right at 4?
No, you can take the time. No, not an issue.
Okay. So maybe I'll
Thank
extend at least few minutes beyond 4 p.m., given that we
Yes,
are
yes.
running a little bit late today.
Sure, sure.
Okay, so I think I felt that I kind of abruptly ended my topic of the topic of channel coding that I was covering. So let me actually just quickly say uh, that uh, this topic of channel coding, just like the topic of data compression, is a very, very wide topic. And actually, there are graduate level, full semester long courses with this as the only subject. The name of the subject is uh, error control coding or data compression, etc. Right? So uh, it's not possible to do full justice to the breadth of the topic, given that we have only 1 hour. But the point that I want to convey to you is that a lot of advances have happened to move this blue line, which is the repetition coding performance, to the performance of this red colored theoretical achievable line. This red color is coming from the information transfer rate, which we defined earlier. Entropy of x minus conditional entropy of x given by. That is what this red colored line is. The blue colored line is simply the repetition coding performance. And uh, how to go from the blue to the red is what drove a lot of the advances in terms of channel coding. And in fact, there was another code which was called, skip over all of this, another code which was called single parity check code. All that it does is it takes n-1 bits as input and adds one extra bit, which is the parity bit at the output. That is all that it does. In case of 3/4 SPC code, it will take 3 information bits, add one parity bit, which is simply XOR. So this bit here is showing XOR. And that XOR of M1, M2, M3 becomes P1. And then these 4 bits, M1, M2, M3, and P1 are transmitted as the 4-bit code bits, C1, C2, C3, C4. It turns out that one of the most advanced coding scheme, which is the LDPC code, works on the principle of multiple SPC, single parity check code, and multiple repetition codes, which are the C1, C2, C9 codes. And there are some efficient decoding algorithms, which are called iterative decoding on graph, that have been defined. And they actually iteratively figure out which are the corrupted bits out of uh, 10-bit code word that is received over, let's say, binary symmetric check or binary resistor check. So that is how the low density parity check codes were defined. And today's 5G phones actually implement this LDPC channel. Okay, so LDPC is the latest and the greatest in terms of channel coding technique. Now, in case of channel coding, what we have seen is that if we make R the rate to be close to 1, right, then it means that the code ceases to provide error correction. When R is equal to 1, you are not doing any error coding at all. The bits that you get, you just transmit them, and that's it. When R is, yes, I have temporarily stopped sharing. I'll resume very soon. When R is close to 0, it means that you are doing a lot of error control coding. Like for repetition code, if I make R equal to 1 over 41, then I'm really uh, transmitting very little amount of information, and most of it is just additional parity bits that I added to protect against noise. When you do that, you can reduce the SNR requirement because the error control coding, the channel coding itself overcomes the effect of noise. On the other hand, your data rate requirement goes down. On the other hand, if you make R close to 1, then you can transmit data faster because you are not sending any extra repetitive bits. But then your SNR better be good because you are not having any other protection by this noisy channel coding. So that is the concept with which we begin our next topic, which is the topic of modulation, demodulation, and detection methods, including their performance analysis. Okay, so this is going to be the topic of this set of slides. Originally, the communication systems were analog in nature. We all have heard of AM radio, FM radio, etc. Today's communication systems are almost all of them digital in nature, except the FM radio, which is still surviving. The reason why, okay, so the difference between analog communication method and digital is as follows. In analog radios, the incoming information signal is analog. It gets sent to what is known as a modulator. That is it. There is nothing else besides that. For a digital communications transceiver, which is your cell phone today, or your internet modem or anything, this is the technique that we have seen is implemented. We have looked at source encoding, we have looked at channel encoding. Now we are going to look at modulation block. So the advantage of digital over analog is that in analog system, if there is any noise, then there is nothing else you can do about it because there is no noisy channel coding. Similarly, you cannot do source encoding. There is a technique called encryption which preserves the privacy. You cannot implement that in analog methods. Another reason why digital communication systems are prevalent today is because the computers have become very powerful. All our phones are actually very advanced computers on which such noisy channel coding or noiseless channel coding and even modulation, demodulation can be implemented. So these are the reasons why digital communication systems have won over analog methods. From a performance standpoint, let us see what digital communication systems can do with it. So let us take a look at the error performance chart. The y-axis shows bit error rate, and the x-axis shows SNR. What does this bit error rate mean? Let's say 10 to the power minus 4 means that you transmit 10,000 bits, only one bit is in error. 10 to the power minus 6 means you transmit 10 to the power 6 bits, only one bit is in error. To achieve 10 to the power minus 6 bit error rate for a modulation scheme called BPSK or QPSK, you need SNR of roughly about 10.5 dB, 10.5 decibel scale. If you had 8 PSK, you need 14 decibel scale of SNR to achieve 10 to the power minus 6 error rate. And if you did 16 PSK, you needed maybe around 19 decibels of SNR. Overall, regardless of whether it is BPSK, QPSK, 8 PSK, 16 PSK, by the way, these are the names of different modulation schemes that we are going to understand either today or tomorrow. What happens is that the error rate decrease kind of gradually as you increase the SNR. These are known in the communication parlance as waterfall curves. It seems like the shape that a waterfall takes. Now, remember I just mentioned LDPC codes. I just briefly mentioned it a few minutes back. LDPC codes are a type of this noisy channel coding technique that are so nice and so powerful that they make these error rates go down a cliff rather than go down a waterfall. Okay, so what this light blue or cyan colored curve shows is the error rate of an LDPC code. And what this is able to achieve is that because of this cliff type of performance, if the SNR is on the left-hand side of this line that I have drawn, then practically all the messages that you send through this LDPC technique are not going to be received correctly. Basically, your link is inoperational. On the other hand, if you are on the right-hand side, then all the messages are going to be received correctly. It becomes like a binary on-off type of switch, which was simply not the case for this BPSK, QPSK type of transmission. And this is not just one lone single strange result. This type of cliff in terms of packet error rate or bit error rate or message error rate or block error rate as a function of SNR has been obtained for wide varieties of different modulation schemes, QPSK, 8 PSK, 16 PSK. This we don't know what they mean right now, but just take my word for it that there are different digital modulation schemes, as well as for different coding rates. So these labels are the code rates. Coding rate, you know what it means. Rate 1/3 means that 1 out of 3 bits is the message, the other 2 are repetition bits. Rate 1, 2 means k divided by n is 1/2. K could be 10, n will be 20. K could be 128, n will be 256. Rate 4/5 means k divided by n is 4 divided by 5. If k is 4,000, n will be 5,000. So as you move from 1/3 to 4/5 to 5/6, you are increasing the rate. Remember, as we increase the rate, we reduce the error protection provided by the noisy channel coding, and therefore the SNR goes up. But if you're using QPSK, then you can have all of these different lines over which you can operate. And then if you have, so QPSK will allow you to operate over maybe -2 to +5 decibel of SNR. If you have larger SNR, even more than 5 decibel, then you can go to 8 PSK. And then you can even go to 16 PSK. What do I mean by all this? Remember I said that all of these are to be thought of as cliffs. On the left-hand side, the performance is lousy. You never want to operate on the left. On the right-hand side, the performance becomes nearly error-free. All your messages are almost guaranteed to be received correctly. The way this helps is, in the real life, the signal-to-noise ratio is always going to be variable. You're driving in the car, maybe your car is close to a base station and the SNR is large, but as you keep on driving, the car moves away from the base station, SNR drops. Or maybe you are far away, your SNR is already like -2 dB. When it is -2 dB, you can't do much more than some very small rate. By the way, this gray colored uh, bell-shaped curve is the distribution of the SNR. And so what you will see is that maybe as the car keeps coming closer and closer, you know, नहीं अभी नहीं So you'll see that as the SNR keeps on increasing, your data rate can become, or the channel rate that you can operate at can become larger and larger. The way this helps is that for a particular coding rate and for a particular modulation scheme, as the previous chart showed here, this chart showed or this chart showed, you need a certain SNR, right? On the right hand side of the SNR, you can operate. On the left hand side, you cannot operate. Now, given a particular scheme, let's say BPSK and some particular coding rate, as long as your SNR is on the right hand side, you can operate, and then that will be your achieved rate or achieved capacity or achieved data rate or achieved throughput. Today's communication systems, whether it is 5G, whether it is DVB-S X or DVB-S2X or LTE 4G, what they do is they implement all of these different coding rates and all the different modulation schemes that we're going to consider. Because of which what happens is that, unlike this case where your SNR keeps on increasing, but it doesn't give you any benefit in terms of the achieved rate, as the SNR increases, you go to a better channel coding rate and better modulation that will give you better data rate. The SNR goes even higher, then you go to this purple one. So as SNR keeps on becoming better and better, you can actually throttle the data rate to faster and faster values, right? How will you do that? By increasing the rate. Remember, as you increase the rate, you are reducing the repetitive bits that you're introducing, which means that the information actually gets throttled faster. Other way to do it is by going to what is known as higher order modulation, which is the topic of this particular lecture. The end result is that we are getting higher and higher data rate. Our videos start loading faster, our messages get exchanged quicker. Why? Because our phones are, or our Wi-Fi devices are getting strong signal. SNR is pretty good. Now, what if you start going away from your Wi-Fi router or your phone moves away from the base station? Then suddenly your SNR drops. As the SNR drops, you come down on this purple line, and you can't get that data rate anymore at all. So you go to this cyan colored line, which could be, let's say purple is rate 5.6, cyan could be rate 2/3. Because going from 5.6 to 2/3, you are reducing the rate, means that your throughput has become less. You are introducing more repetitive bits. So your actual information is not being throttled as fast anymore. If the SNR drops further, then you add extra layer of channel coding. You add even more repetitive bits. Maybe you increase the repetition rate to be even smaller value. I mean, decrease it so that for smaller value. The benefit is that with that extra layer of protection, you can tolerate lower SNR, but the achieved rate becomes smaller. If the SNR still keeps on falling, you can go to lower and lower data rates, all the way to maybe this blue one, where you've gone maybe to a rate as low as 1/3 or even less. Now, your achieved rate is pretty small because most of what you are transmitting in terms of bits are those repetitive bits. Hopefully, you are not doing rate 1/63 or rate 1/41. That would be too low. But even rate 117 or 19, which actually happens in today's wireless technologies, still really affects your throughput. You are not able to send as much information at all. That is the price you pay, but the benefit you get is that now your communication link still survives even though the SNR is very lousy. Okay, so that is the idea behind today's communication transceivers. What they do is they stay on the top of this peaks as the SNR reduces and increases, reduces and increases. They go up like this and they fall down like that. Go up, fall down, go up, fall down. Only when SNR goes below this leftmost point is when the receiver gives up and says that the link is dead. Okay. So in terms of that chart that we were looking at, uh, this is what is happening, right? So the blue is the one that gets realized. The red ones are not realizable. You can't uh, have successful communication for the red colored lines. But as SNR increases, you are able to increase to higher and higher coding rates. So this is something that can happen only in a digital communication system which does this noisy channel coding and modulation schemes. This is not possible in analog systems. Okay, so I'll skip over maybe some of these charts and then look at now look at one primary role of what is known as the modulation block. Okay, so So this we talked about source encoding, channel encoding, etc. We are now going to focus on this modulation and demodulation block. In some textbooks, some authors like to combine modulation with frequency up conversion and demodulation with frequency down conversion. Um, it's either way, they both are kind of very critical operation that a communication system performs. But we will maybe first look at this operation of frequency up conversion. What it is and why it is needed, right? So that is what we will look at. So basically, as you know, today's communication devices, almost all of them, operate at radio frequency. Right? That is where the word radio frequency came, because the original radios were using those frequencies. It's like a circular definition. Uh, so what is the reason? The reason that our phones and our satellites, etc., they use certain range of frequencies is because uh, those particular electromagnetic waves in that range of frequencies transmit actually very, very well. Okay. How to, what type of comparison can I give? So suppose you have a roller stone, right? Like the cylindrical stone, and you want to roll it over a surface, right? Let's say the roller stone is rough and the road or the surface over which you want to push it is also rough. And so you try to move it as far as you can, and so you push it hard. But because there is a lot of friction, that roller stone, that cylinder will keep on rolling for some time before it will come to a halt. It won't go very far. But now, let's say next day you come better prepared. What you do is, first of all, that surface of the road, you polish it, you rub it, and you make it very, very smooth, almost like a glass. Maybe you sprinkle a little bit of oil on it. And then even the roller stone that you have, that also you polish it, you make it really shiny, very smooth. And now you roll the stone with the same force. Suddenly you will see that that rolling stone goes maybe 10 times, it traveled 10 times longer distance before it stopped. Something like that happens in the transmission of the waves. There are certain waves which don't propagate very far. Audio waves, sound waves are like that, right? They don't travel too far in the atmosphere, which is actually good because otherwise our ears will be bombarded with a lot of noise all the time. Electromagnetic waves, especially at certain frequencies, are not like that, especially when they're transmitted using antennas. They, for this environment, even the outer space, vacuum, etc., they roll like that smoothened, oiled rolling stone. They just keep on traveling on and on and on. And that is the reason why our communication devices put the messages that we want to transmit on this electromagnetic waves. So that I can be sitting here in my office and I can suddenly make a phone call, and the signal that is generated by the tiny battery of my phone will still have enough traction to go to the antenna of a base station, which might be 2 kilometers away, right? Or 3 kilometers away. That is possible simply and only because the phone doesn't transmit my voice in the manner that it was generated, which is the auditory signal. It converts that audio into an electromagnetic wave. And it puts my voice information, or if I'm doing internet browsing or anything else, it puts that data on top of that EM wave, simply because it propagates well. More specifically, this EM frequency of electromagnetic wave, has fundamental connection with the size of the antenna that you need in the path loss that the signal experiences. So if suppose you say that my phone needs to be miniaturized, I cannot have a very big antenna. Well, then maybe you, instead of using 1,000 megahertz, 100 megahertz frequency of EM frequency of 100 megahertz, maybe use frequency of 2,000 megahertz, 2 gigahertz, 2.5 gigahertz. As you increase the frequency, the antenna size becomes smaller. The other thing that is beneficial of this type of transmission is that it allows us to do what is known as frequency division multiplex. We can place the signal at the desired portion in the spectrum. We will quickly see that in the next slides. Okay, now that we say that we are going to be doing this electromagnetic wave-based transmission of the information, what we'll see is that our transmitted signal can be written in terms of that sinusoidal waves as S of t equal to Si times cosine of 2 pi f ct minus SQ times sine of 2 pi f ct. This is a very general way of writing the transmitted signal. Okay. What is f of c? That is the frequency of electromagnetic wave, whether it is 100 megahertz or 500 megahertz or 2 gigahertz, etc. What is Si and SQ? Those are going to be our modulation symbol specifiers. Remember, I was throwing a lot of names at you: BPSK, QPSK, HPSK, etc. in some previous slide. So those modulation schemes are going to define what Si and SQ are. Basically, Si and SQ contain the information. Ultimately, they are the bits. But we can't transmit bits using electromagnetic waves. So what this modulation scheme does is it takes some bits, converts them into Si and SQ. And then those Si and SQ then become voltages. Those voltages are used to amplify this cosine and sine. And then ultimately they get combined like this, and then S of t gets transmitted. Okay, so this is the general notation of the output of a block which comprises both modulation and frequency up conversion. Okay. Remember, I said that some authors call modulation as well as frequency up conversion together collectively as modulation block. So this equation actually represents that. it has both frequency of conversion as well as modulation. Now, this equation 1 is completely and entirely identical to equation 2. If you do just a little bit of complex algebra, complex math, we'll see that if I expand out Si plus Js cube, which is a complex number, multiplied by exponent of J 2 pi f ct. By the way, exponent, do you know how to write exponent of J 2 pi f ct in terms of cosine and sine? The real part of this is cosine, imaginary part of this is sine. Okay, so that is what this exponent J 2 pi f ct is. Take the product and take real part, it becomes exactly this. So this is called the complex envelope representation. And then in this context, you will see that this Si and Sq became kind of the real and the imaginary part of a complex number. And then finally, the third representation is called magnitude and phase representation. These three are completely equivalent representation of the same exact signal, S of t. You can take this first equation and write it also as A times cosine of 2 pi f ct plus theta. What is A? A is the magnitude of S of t, square root of Si squared plus Sq squared. And theta is tan inverse of Sq over S. The phase of S. Sometimes this is also called the polar representation. Okay. Now, I say that these equations contain both modulation as well as frequency of conversion. So, to explain that, to explain what I mean by that, let us take this equation number 2. For the time being, let us ignore this operation where I take the real part of a complex number and just consider the complex number in the bracket, curly bracket. Okay. Si plus JSQ, we haven't defined it yet. We haven't said what it is so far, except okay. So Si plus JSQ is going to be defined by our modulation scheme. But what we'll assume is that if I perform some type of Fourier analysis, Fourier transformation, it will have energy content centered at 0 hertz. Okay, let us assume that. So in order for me to proceed, I think I'll just very quickly define Fourier transformation. So it's defined in a manner like this. And there is a modulation of theorem of Fourier transform which says that whenever a signal st is multiplied by exponent of j 2 pi f t, its Fourier transform moves by f of c hertz. So this is the modulation theorem. And then there is some theorem called complex conjugate symmetry theorem. If you have already studied Fourier transformation, this all should come easy to you. If you have not studied, then you have to just take my word for it. Okay, it's not possible for me to explain the concept behind these theorems, except maybe I will show it visually what is happening. That the actual information, once you convert bits into modulated symbols after some operation which is known as pulse shaping, which we won't get into in this series of lectures. You take its Fourier transform, as I was saying, it will be roughly centered at 0 hertz, and it will have some bandwidth of capital B hertz. Now, what your phone does today is that whenever you speak something or whenever you have some images to send, some WhatsApp messages to exchange, all those information gets converted into bits. Those bits get converted into this symbols S equal to Si plus J is 2. And if you actually do the Fourier analysis, they will appear to be centered at 0 hertz. Now, you can't do much with a signal which is centered at 0 hertz. It would be like that uneven, rough rolling stone over a rough road. Right? It won't travel too far. If you are not interested in sending the signal long distances, then maybe it's okay. Maybe you stop there. You don't do anything else. But today, almost all the time, we are interested in long distance communication. Even when we are doing Wi-Fi, we might be sitting just in the next room, but that next room is still at least some few meters away from the Wi-Fi router. So if you just try to push this signal at 0 hertz, it won't even travel those few meters. It will die down very quickly. So the idea is that you make use of this modulation theorem of Fourier transform. You take S of t and multiply with exponent of j 2 pi fct. What is Fc? It is what is known as carrier frequency. It could be, as I said, 2.5 gigahertz, 5 gigahertz, 6 gigahertz in 5G and possibly more so in 6G. Frequencies are going to be even more than 6 gigahertz. It is known as some FR2 operation. Sub 6 gigahertz is FR1, above 6 gigahertz is FR2. Multiply, and then suddenly the spectrum moves to FFC hertz. That is what the frequency up conversion does. Translates the signal from 0 to FFC hertz. Okay, and then there is this operation of taking the real part, which creates the mirror image. That let's not get into it as of now. Now, once the signal reaches the receiver has to bring the signal back to 0 hertz. The reason is because our ears and our eyes and our brains cannot make sense of something which is oscillating at such high frequencies. Forget about 5 gigahertz, even something which is oscillating at 100 kilohertz, we can't hear that. Our ears can hear only frequencies which are below, I think, about 20 kilohertz. Something could be very loud, but if it is above 20 or 30 kilohertz, we won't hear it. So this signal has to be brought back to 0 hertz. That is frequency down conversion. So all that receiver does is, just the way transmitter took this and moved here, the receiver takes this and moves it back. That's all. Obviously, the actual hardware requires a lot of smart design, but mathematically, this is all that is happening. Now, one other thing, remember I said that you can do frequency division multiplexing because of this operation, is that suppose there are one base station is simultaneously connected to, let's say, 4 or 5 different phones. The base station will allocate slightly different frequencies to those phones. And so because of that, the transmissions remain non-overlapping in spectral domain, right, as you can see. And so that allows multiple active transmitters to use the communication channel simultaneously and without any interference among each other. That is another key reason why this frequency translation is very, very useful. One example of this is that in case if you have used FM radio, uh, these different FC1, FC2, FC3 are frequencies of different FM radio stations. And as you tune your radio from 88.5 megahertz to 108.5 megahertz, the radio picks up station number 3, then it goes to station 2, station 1, and so on and so forth. So while you are listening to station 1, you don't worry about station 2 or station 3 because their spectrum don't overlap with station 1. So that is another reason why this operation is very useful. Okay, let's see. I have a representation of modulation in terms of linear algebra, but I think in terms of the syllabus of this course that has been given to me, the linear algebraic representation of frequency up conversion, down conversion is not part of the syllabus. So I'm going to skip over the slides. They are very, very elegant and very interesting mathematical topics in themselves. But for the sake of time and for the sake of covering the topics that are given, let me move forward. Okay, so skip over all of this content. Slides are available to you and you can view them on your own. Or tomorrow, if you have some extra time left at the end of tomorrow's lecture, we might come back to this. Okay, so with that, let us just very quickly look at a very simple digital modulation scheme that is known as binary phase shift keying. And also we will look at another very simple scheme called on-off keying. And here we are going to so maybe some of these BPSK OOK concepts we have mentioned earlier. But here we are going to consider a very simple representation of these schemes. Okay, so I'll go maybe continue for maybe 5 more minutes before I stop for today. So what is BPSK? That's the basic concept of digital modulation systems. Remember we said that a very simple model of a communication channel is binary symmetric channel. Another pretty simple model was binary resonance channel. But there, the entities that were being communicated were bits. There were zeros and ones, right? Now, zeros and ones are mathematical entities. You cannot really have anything like zeros and ones. 0 and 1, these are all numbers. And numbers are not physical. Your phone cannot generate 0. Your phone cannot generate 1, right? You can't just suddenly turn on your phone and out pops something like 1. In fact, 1 is not even any real thing. I mean, I can touch this table that is in front of me. 1 is nothing that can be touched. 1 or any other number, 0 or anything else. And so real world communication channels actually require real signals. And that is where those electromagnetic waves come into play. But we are, as I said, we skipped over some of those linear algebraic representations. But suppose we say that we did this frequency up conversion and then we did frequency down conversion. And so as a result, uh, we are not going to worry about this 2 pi fct part of it, right? Because when we do frequency up conversion, we multiply by exponent of j2 pi fct. When we do frequency down conversion, effectively multiply by exponent of minus j2 pi fct. Plus j2 pi fct moves from 0 hertz to fc hertz. Multiplication with minus j2 pi fct brings it back to 0 hertz. So that effect kind of cancels out. So what we are going to look at is just the remaining part, Si plus Sj is Q, which is what the modulation block generates. For the BPSK, SQ is always 0. Okay, that's why it's one of the simplest modulation squares. Even the on-off key, SQ is 0. So only thing that we have to see is what is Si. So for BPSK, this SI now, remember, SI is multiplying with this cosine and sine and all that, right? So SI is actually a voltage now. It is not some logical numerical representation. Something that is physical, that your phone generates. How does your phone generate that S of I? Or now we are going to just call it maybe S. Okay, so as we said, the phone gets zeros and ones. Those zeros and ones flow through maybe the source encoding block, which is the Lempel-Z coding or Huffman coding. And then those bits then go to channel encoding. The output of channel encoding is still in terms of bits. Those bits come to this BPSK modulator. So input is zeros and ones. And all that BPSK modulator is it takes 1 and maps it to plus a volt, 0 maps it to minus a. That is all that it does. Okay. And then remember that is SI. That gets multiplied by cosine of 2 pi fct. That is frequency up conversion. At the receiver, the frequency down conversion happens. Assuming that down conversion is exact inverse of up conversion, that cancels out. So that is why we are going to ignore all of that and we are just considering the simplified scheme. And say that the transmitted symbol is S, either plus A or minus A, depending on whether 1 or 0 was transmitted. The channel now introduces a voltage noise. Maybe it has some variance sigma n squared. Maybe it is Gaussian distance. The receiver gets superposition of S plus N. And then that goes to the detector or the demodulator of BPSK, whose output is again either 0 or 1. Hopefully that matches 0 or 1 sent by the transmitter. On-off keying is very similar, except x equal to 0 gets mapped to s equal to 0. Here it was s equal to minus a, here is equal to s equal to 0. Basically, when x is equal to 1, you turn on the transmitter. When x equal to 0, you switch it off. That is what s equal to 0 means. Okay, so this is where I will stop for today. And then when we meet tomorrow, we will see how to do detection of this simple BPSK schemes, BPSK and on-off keying schemes. And then later on, a little more advanced schemes will be the topic that we'll cover.
Thank you, sir. Thank you very much. So we are closing us. So do you want, sir, to give the answer? There are some questions in the chat box. I don't know if you have.
Okay, so